Good day, everyone. Today, we'll dive into one of the most geologically dynamic regions in the world, which is Indonesia. This presentation will walk us through the fascinating tectonic framework that shapes this vast archipelago. We'll be covering key topics such as the architecture of Indonesia, the Indo-Australian subduction zone, major tectonic structures both around and within the region, the unique role of the Moluccas Sea Plate, and finally, we'll explore the tectonic evolution of Indonesia from the past to the present.
Let us now discuss the architecture of Indonesia. Indonesia is the largest archipelago, which is made up of 5 major islands and 30 smaller island groups. The 5 major islands are Borneo, Java, Sulawesi, Sumatra, and Western New Guinea. Indonesia serves as a crossroad between the Pacific Ocean and the Indian Ocean, and it bridges the two continents of Asia and Australia. We will now discuss the major plates that make up or form Indonesia. There are 3 plates that are responsible for the formation of Indonesia and its islands: the Eurasian Plate, the Pacific Plate, and the Indo-Australian Plate. The Eurasian Plate is located at the northwest side of Indonesia, the Pacific Plate is located at the east side, and the Indo-Australian Plate is at the south side. The Indo-Australian Plate moved northward and subducts beneath the Eurasian Plate. The subduction zone can be traced from the northern tip of Sumatra until the lesser islands, creating a deep submarine trench. The Pacific Plate moves southwest under the Eurasian Plate. This subduction created the formation of volcanoes in the North Sulawesi, Sangihe, and Halmahera. Next are the deep trenches of Indonesia. The Java Trench is formed as the Indo-Australian Plate subducts beneath the Eurasian Plate. It is located about 305 kilometers off the southwestern coast of the islands of Sumatra and Java, and has a depth of approximately 7,290 meters, making it one of the deepest trenches in the world. Next is Timor Trough. It is formed due to the Australian Plate subducting and the collision between the Australian continent and the Banda Arc. The trough is located at the south side of Timor Island. Timor Trough has a depth of approximately 3,300 meters. Lastly, we have the Tanimbar Trough. It is formed the same way as the Timor Trough. Collision between the Australian continent and the Banda Arc led to the formation of the Tanimbar Trough. It has a depth of approximately 3,000 meters and is located southeast of Banda Arc between the Timor and Aru troughs. Next, we will now discuss Indonesia's landforms. So, may tatlong plate ang nagko-contribute sa landforms ang meron sa Indonesia. Una ay ang Southeast Asian Plate. Ang ambag nito ay yung fault zones gaya ng Red River, Wang Chau, and the Three Pagodas. This influence seismic and volcanic activity in Indonesia. The interaction among plates leads to the process of subduction and collisions resulting in volcanic eruptions and earthquakes. Next is the Australian Plate collision. Yung northward movement ng Australian Plate ay nag-cause ng abduction at yung pag-uplift ng mga mountain ranges, especially sa Timor at Samba. Subductions at collisions resulted in the formation of mountain ranges at uplifting land masses. Finally, yung Pacific Plate, yung westward movement ng Pacific Plate ay nag-influence sa landform development sa Northeast Indonesia, including the Aru Basin. Yung subduction process, it contributes to the formation of island arcs, which are chains of volcanic islands along the edge of subduction zones. It can also create a deep oceanic trenches, which are long, narrow depressions on the ocean floor. Moving on are the landforms in Sulawesi. Sulawesi is one of the larger islands in Indonesia. Located in the central part of the archipelago, it is found between the Pacific and Australian plates. Sulawesi is believed to have been formed by the collision of terrains from the Asian plate and the Australian plate, with island arcs previously in the Pacific. The island of Sulawesi has four peninsulas. The northern central part of the island consists of mountains. The northern Minahasa Peninsula, extending north to the Sangihe Islands, is known for its active volcanoes, including Mount Lokon, Mount Awu, Saputan, and Karangetang. Sulawesi is prone to earthquakes due to its tectonic origins, with various fault lines scarring the land.
Indonesia sits at the heart of one of the most geologically active regions on Earth, all because of the dynamic movement of the Indo-Australian plate. This tectonic plate has shaped not only the land but also the lives of millions across Southeast Asia. From its origins as part of the ancient supercontinent Gondwana to its ongoing collision with the Eurasian plate, the Indo-Australian plate has played a major role in forming mountains, building islands, and triggering some of the world's most powerful earthquakes and volcanic eruptions. This tectonic journey explains why Indonesia is both breathtakingly beautiful and dangerously active. So let's first discuss the Indo-Australian plate origin. Around 550 to 180 million years ago, Earth's continents were grouped into massive landmasses called supercontinents. One of these was Gondwana, which included modern-day South America, Africa, Antarctica, Australia, and the Indian subcontinent. Back then, India was located far south near the South Pole, sharing connections with Antarctica and Australia. As tectonic forces between the Earth's mantle acted on Gondwana, it started to break apart around 130 million years ago. India detached and began drifting rapidly northward. So, yung bilis ng movement ng India was about 15 to 20 centimeters per year, which is unusually fast for tectonic plates. Along the way, India crossed the ancient Tethys Ocean. After millions of years of northward movement, the Indian plate finally collided with the Eurasian plate around 50 million years ago. Unlike oceanic crust na madaling magsabdak, continental crusts are buoyant. So, instead of one plate simply sinking, intense compression occurred. This collision uplifted rocks and sediments, forming the Himalayan mountain range and the vast Tibetan plateau, which are the structures that are still growing today. So, the Indo-Australian subduction caused distinct effects in Southeast Asia, especially in the Indonesia. This subduction is the driving force behind Indonesia's active volcanoes, earthquakes, and unique geography. So one of these effects was the formation of volcanic arcs. As the oceanic portion of the Indo-Australian plate subducts, it melts upon reaching hotter regions of the mantle. The generated magma rises to the surface, forming volcanic arcs. Example nito ay ang Sunda Arc sa Indonesia, where we find famous volcanoes like Mount Krakatoa and Mount Merapi. Another effect of the subduction is the creation of islands. Over millions of years, volcanic activity at these arcs built many of Indonesia's islands. The islands of Sumatra, Java, Bali, and the Lesser Sunda Islands were primarily created by volcanic eruptions and tectonic uplift. Kaya nga, Indonesia is often called the land of volcanoes. The immense compressive forces at subduction zones also lead to mountain building, a process called orogeny. In regions like Sumatra, crustal thickening and faulting uplift mountain ranges such as the Barisan Mountains. Dito makikita kung paano nagbabago ang landscape over time dahil sa tectonic forces. In terms of the geological phenomena, it will be discussed later on, which is also one of the effects of the Indo-Australian subduction. So this diagram shows the Sumatran subduction zone where the Indo-Australian plate is subducting beneath the Eurasian plate, especially the Sunda plate. As the dense oceanic crust moves northeastward, it sinks into the mantle, forming features like the Sumatran Trench, Fore-Arc Basin, Volcanic Arc, and Back Arc Basin. Sa madaling salita, dito nagkaroon ng major geological activities tulad ng formation ng mga volcanoes and frequent strong earthquakes. The subduction leads to the partial melting of the mantle, producing magma that rises to form volcanic mountains like the Barisan Range. Major seismic activities are concentrated along the megathrust fault, which can generate devastating events such as the 2004 Indian Ocean earthquake and tsunami that will be included into the discussion of the geological phenomena. So overall, the continuous interaction between these tectonic plates constantly reshapes Sumatra's geology, landscapes, and ecosystems. So now let's proceed to the geological phenomena, which is one of the effects of the Indo-Australian subduction. So the subduction of Indian plate beneath the Eurasian plate is the continued movement of the Indian plate under the Eurasian plate that fuels seismic and volcanic activities across the Indian Ocean and Southeast Asia. Hindi lang ito basta-bastang ordinaryong collision. This is a deep, ongoing geological battle that shapes entire regions. This leads to massive earthquakes and tsunamis, including the 2004 Indian Ocean quake that killed over 230,000 people, which is what I mentioned earlier. So the full details about it is on December 26, 2004, the sudden slip of the Indo-Australian plate under the Eurasian plate triggered a magnitude of 9.1 to 9.3 earthquake west of Sumatra. The earthquake unleashed a massive tsunami that devastated coastal communities around the Indian Ocean. It was one of the deadliest natural disasters recorded in history, highlighting the immense danger of subduction zones. Another effects of the subduction of Indo-Australian plate is the zone where the plates meet accumulates extreme stress over time, which is kapag hindi na kaya ng rocks na mag-hold ng stress, sudden ruptures releasing enormous energy as earthquakes. This is what happens along megathrust faults like the Sunda megathrust in Indonesia. So this map shows the India plate, Burma microplate, and Sunda plate along with important geological features like the Sunda Trench and Great Sumatran Fault. May mga iba't ibang markings din, such as the red line, which symbolizes generalized plate boundaries. The blue line shows thrust faults, and purple lines represent strike-slip faults. Yung mga arrows naman, nag-i-indicate yan ng direction and speed of the plate movement. And the yellow star marks the location of the earthquake that happened on December 26, 2004. Habang yung small triangles naman, nagre-represent siya ng active volcanoes near the plate boundaries. So as said earlier, the subduction is still continuous, and the pressure build up underneath Indonesia also feed volcanic systems like Mount Merapi. This stratovolcano is highly active, erupting regularly. So one of its most devastating eruptions occurred in 2010, killing hundreds and displacing thousands. And yung map na nasa gilid shows the eruption of Mount Merapi in Indonesia on October 26, 2010. Yung red triangle ang nag-represent ng eruption ng Mount Merapi. The eruption killed 29 people and forced the evacuation of 22,000 to 30,000 residents, though around 7,000 stayed within the 10-kilometer evacuation zone, which the evacuation zone marked on the map was the blue circle. And the red lines are the roads The black lines are the provincial boundaries, and other volcanoes, which are active volcanoes, was represented by green triangles. And the Solfatara stage, which are the black triangles, are also marked. The key cities like Yogyakarta, which was represented in black dot, are also labeled, and the inset map shows Java's high population density, highlighting the potential danger of future eruptions. So overall, the subduction of Indo-Australian plate created a big impact on the evolution of the Indonesia, which is the Indonesia that we see and what we know today.
Major tectonic structure around and within Indonesia. In Indonesia, island arcs form the structural framework for volcanic and banda arc, while basins are the products of tectonic activity. Arcs in basins contribute to orogenic processes through subduction, collision, and faulting. Arcs and basins around and within Indonesia. Indonesia's arc includes volcanic arc and banda arc. Volcanic arc formed due to subduction of the oceanic plates beneath the continental plate. Sunda Arc is the major volcanic arc stretching from Sumatra through Java and continuing into Bali, Lombok, Sumbawa, and Flores. These arcs are highly active, hosting frequent volcanic eruptions and earthquakes. The orogenic belts that occur is the Sunda orogeny and parts of the Banda orogeny, most closely associated with volcanic arc. Next is the Banda arc. It is a U-shaped arc resulting from the complex collision between the Australian plate and Southeast Asian microplates. It is divided into inner volcanic arc, outer arc ridge, arc-related basins, and trench system. It is defined by the Banda orogeny caused by continental arc collision. Next is the Indonesia's basins are mostly tertiary in age and form from different tectonic settings, and we have back arc basins. Back arc basins form behind volcanic arcs due to slab rollback or extension. It is also productive for hydrocarbons. It includes Central and South Sumatra basins, Sunda Basin or the West Java, Northwest Java Basin, and East Kalimantan Basin. It is characterized by thick sedimentary sequences up to 6,000 meter and high potential for oil and gas. The associated orogenic belts here are Sunda, Sulawesi, Banda, and Melanesian orogeny because of tectonic processes. Next is the orogenic belt. Orogenic belt develops when a continental plate crumples and is uplifted to form one or more mountain ranges. This involves a series of geological processes collectively called orogenesis. According to Simanjuntak and Barber 2016, there are six main Neogen orogenies or orogenic belts in and around Indonesia. First is we have Sunda orogeny, Barisan orogeny, Talaud orogeny, Sunda Sulawesi, Melanesian orogeny, and Banda orogeny. First is Sunda orogeny. It is located in Java, formed by subduction of the Indian Ocean plate beneath Sundaland. Subduction-related extension formed rifted basins behind the volcanic arc. The weather thrust marks the potential reversal of subduction polarity. The Barabis-Kending thrust system reflects back arc compression and active folding. According to Simanjuntak and Barber 2016, the Barabis-Kendeng thrust is traced from Sunda Strait or the West Java, across Java and Bali Basin into the Flores Thrust or the north of Flores, and possibly continues eastward as the Wetter Thrust. So while there is a structural continuation, the tectonic context changes from the Sunda orogeny to the Banda orogeny as we move east. It is also built on continental crust in Java and accretionary complex in East Java. There are also active volcanoes like Merapi, Semeru, and Rinjani. Its impact is high seismicity because of frequent earthquakes and volcanic hazard. The Sunda orogeny is also responsible for the volcanic inner arc in western and central Indonesia. Next is the Barisan orogeny. It is located in Sumatra, caused by oblique convergence between Indian Ocean Plate and Sundaland. This creates a strike-slip movement along the Great Sumatran Fault or the Barisan Fault Zone. Uplifted volcanic arc with significant geothermal and seismic activity. There are also numerous pull-apart basins like Lake Toba at the site of a supervolcano. Next is the Talaud orogeny. It is located in the Molucas Sea between Sangihe and Halmahera. The arc collision between the Sangihe Arc and Halmahera Arc. The Molucas Sea Plate is subducted beneath both the Halmahera Arc in east and Sangihe Arc in west. Then, the Talaud Mayo Ridge is formed because of an uplifted zone between the arcs. Next is the Sulawesi orogeny. This belt formed by collision of microcontinents like Buton, Tukangbesi, and Banggai Sula with the East Sulawesi Ophiolite belt. Movement along the Sorong Fault system transported these microcontinents westward. The Palo-Coro Fault is the tectonic boundary in Sulawesi orogeny and it is a left lateral strike-slip fault causing ongoing deformation, earthquakes and basin formation like Lakes Poso and Matano. Next is the Banda orogeny. This is a continent arc collision between the Australian plate and the Banda arc. Compression leads to folding, thrusting, and uplift. As compression continued, the volcanism in Alor and Wetar had ceased. The Wetar thrust formed possibly indicating subduction reversal. It means an actual change in the direction of subduction due to tectonic events like a collision. It is also impact is active deformation and seismicity. It affects the volcanic arc in eastern Indonesia, where subduction and volcanism have been disrupted by collision with the Australian continent. Next and lastly, the Melanesian orogeny. It is caused by the collision of northern Australia with the volcanic arc on the Philippine Sea Plate. Because of the collision, it occurs in the massive uplift of central ranges including Puncak Jaya, the highest peak with an elevation of 4,884 meters in Southeast Asia. It includes major strike-slip fault systems like the New Guinea Mega Shear and Sorong fault systems.
And now, the discussion will focus on what active faults are there in Indonesia. And as seen in this figure or in this geologic map of Indonesia, the archipelago is laced with several major active faults that stretch across its island. And this only highlights just how complex and geologically active Indonesia is. And each red line or red arrow you see here marks faults or the fault zone, wherein those are areas where the earth crust is shifting and building up pressure that can be suddenly released in the form of large or powerful earthquake. And these include the well-known faults like the Sumatra, Lembang and Banyuma in Java, the Palu Coro and Matano in Sulawesi, the Timor, as well as the Irian and Ronsiki in Jaya. And in this report, we will explore this fault zone in more detail. First, let's discuss the Sumatra Fault Zone. And it is made up of approximately 20 N-echelon segments and strikes north 320 degree to 330 degree east. This fault zone runs along the entire 1,600-kilometer long Bukit Barisan mountain ranges on the west side of the islands. And the Sumatra Fault, is also known as the Simangku Fault and is a large strike-slip fault running the entire length of the island of Sumatra. And that along this fault zone, it features several pull-apart basins which are associated with volcanic activity observed along the fault line. And so since it is associated with volcanic activity, historical records and modern seismic monitoring shows that this fault has been produced numerous large earthquakes over the past years or past history. So, meaning it possesses a significant seismic hazard to the regions of Sumatra. And now, let us discuss one of the most closely watched fault lines in West Java, which is the Lembang Fault, located 10 kilometers north of the city of Bandung on Indonesian islands and Java. And this fault stretches for about 29 kilometers and is considered an active fault, meaning it still has the potential to generate earthquakes because no major earthquakes have been recorded along the fault line in history, or that it has not yet released a large earthquake for hundreds of years. But still, expert believes that this fault has the potential to produce a magnitude of 6.5 to 7 earthquake in the future. And next to this, it is the Banyumas Fault Zone, located in the Banyumas Basin, which is a sedimentary basin in northern part of the central Java province, Indonesia. And when we say the Banyamas Depression, is just equivalent of Banyamas Fault Zone. Also note that this fault zone is made up of several smaller faults that are active, meaning they can also move and they can still cause an earthquake. And even though it is not as well known as other big faults like the previous one, which is the Labang fault, the Banyamas fault zone is still important because it runs close to many towns and cities. And still, scientists or experts believe that movements along this fault could trigger moderate to strong earthquakes in the future. So it has been carefully monitored as well. Now moving forward to the Palu Coro Fault Zone and was formerly known as Grabenposa Saracena. This fault strikes south to southeast and stretches from Palu Bay toward south to southeast for 300 km on land, while its 400-kilometer long submarine extension in the Gulf of Boone appears to be indicated by bathymetry, according to the study of Tigia and Zakaria 1974. And on September 28, 2018, this fault, the Palu Coro, it caused an earthquake known as the 2018 Sulawesi earthquake and tsunamis, having a magnitude of 7.5 to 7.6 that struck about 70 kilometers or 43 miles from Palu, the capital of Central Sulawesi. And it was felt as far as the Samarinda in East, Kalimantan, and even Tawau in Malaysia. And this major quake was preceded by a series of foreshocks, including a magnitude 6.1 tremor that occurred earlier on the same day. And this earthquake, it badly damaged Palu and killed thousands of people. And by this, it's just showed how powerful and dangerous this fault can be. Moreover, the Matano Fault Zone, which is a major active left lateral strike slip fault in Sulawesi, and it's trending west to northwest to east to southeast, and it stretches about 190 kilometers, starting near the southern end of the Palu Coro Fault and reaching Colono Bay on Sulawesi's east coast. And no earthquake has been recorded along the Matano Fault Zone for at least 200 years. Next one is the Timor Fault Zone, wherein we will discuss the five major fault zones that move laterally and were probably generated by the July 13, 1975 earthquake in Western Timor. And the figure here shows those five major faults. Fault 1, which is dextral motion, is shown by sigmoidal gases in soil at Complong Market. Fault 2, sinister slip, is suggested by an echelon arrays of gases in soil. Fault, Fault 3, left slip in northwest direction, is shown among many other phenomena by a deformed brick and mortar wall of the hospital at Lili. Fault 4, right slip, is indicated by 5 cm offset of a weir and by marking on a fault plane cutting alluvium. Fault 5, left slip, is indicated by an echelon in sigmoidal gases and by drag folds in alluvium at the banks of the Owasau River. Lastly, We have here the Irian Fault Zone and the Ransiki Fault in Bird's Head of Irian Jaya. But first, let's discuss the Irian Fault Zone. And according to Weiser and Herm 1962, the Irian Fault Zone is described under the name Sorong Fault Zone, and it marks the boundary between the Halmahera Plate and the Bird's Head Plate. It also stretches westward for over 800 kilometers or more than 500 miles from Telok Sarera all the way to the Banggai Islands. And the Sorong Fault Zone is one of the two major faults formed by the collision of the Australian and Pacific plates, wherein the other one is the Ramo Markham Fault Zone. And last to this is the Ransiki Fault, which it strikes northwest trending strike slip fault located in the northeastern Bird's Head Peninsula of Papua or West Papua, Indonesia, and may be traced on land for a distance of about 70 kilometers. And the map here shown highlights the location and geological setting of the said two faults, and it includes also a variety of rock types, which shown in the figure, and it is in different colors.
So after knowing the major tectonic structure around and within the Indonesia, let's dig deeper into how unique Indonesia is. Now, we will discuss about the Molucca Sea Plate. But before that, I'll discuss first the geologically fascinating and complex area in Southeast Asia, the Molucca Sea region, also known as the Molucca Sea Collision Zone. This region lies at the crossroads of three major tectonic plates: the Eurasian Plate, the Australian Plate, and the Pacific Plate, particularly through its interaction with the Philippine Sea Plate. The area's complexity arises mainly from the intense collision and subduction occurring here, especially involving the Molucca Sea Plate, which is now being consumed from both sides. So this cross-section illustrates the unique tectonic settings beneath the Molucca Sea region, where two oceanic plates, the Sangye Plate and the Halmahera Plate, are both converging and subducting toward each other. This rare double subduction system results in collision complex at the center. The Molucca Sea Plate is a small oceanic plate situated in northeast Indonesia, specifically between the Sanghe Arc to the west and the Halmahera Arc to the east. This area is geologically chaotic, described in studies as a tectonic melange, a messy mix of different rock types often formed under great tectonic pressure. In 3D seismic tomography models, the Molucca Sea Plate appears as folded or inverted U or V-shaped slab, a clear visual indicator of it being pulled in both directions. It is currently almost completely subducted, squeezed between three converging giants, the Pacific, Eurasian, and Australian plates. Due to its unique tectonic setting, the Molucca Sea has become one of the most seismically active regions in the world. So this diagram or this cross-sectional diagram shows the tectonic setting beneath the Molucca Sea, where the Molucca Sea Plate is being subducted into two opposite directions beneath: the Sangye Plate to the west and the Halmahera Plate to the east. So here are the key features of Molucca Sea Plate. The Molucca Sea Plate is sandwiched and pulled downward by opposing subduction forces. The collision complex above marks the zone where crustal materials are squeezed and deformed. And lastly, this system occurs within the asthenospheric mantle, highlighting deep mantle interaction. So why does this matter? This is a rare tectonic configuration, a complete oceanic arc-arc collision. It also explains the high earthquake and volcanic activity in the region. It also helps us to understand how island arcs evolve and oceanic crust is recycled into the mantle. So this figure explains the high earthquake and volcanic activity in the region. The red dots indicate shallow earthquakes. These are mostly concentrated in the central Molucca Sea area beneath the Mayo Talud Ridge and the Gorontalo Basin. The orange dots indicate intermediate earthquakes that are mostly concentrated beneath the Sanghe and the Halmahera. The yellowish and blue dots indicate deep earthquakes that are concentrated in the Sulawesi Sea area. So, one of the most unique features of this region is the phenomenon called the double subduction. This occurs when two Benioff zones or earthquake-generating subduction zones dip in opposite directions. In the case of Molucca Sea Plate, it subducts westward beneath the Sanghe Arc at an angle of about 30 to 40 degrees and reaches up depth up to 500 kilometers, and eastward beneath the Halmahera Arc at an angle of about 45 degrees and reaching depths up to 230 kilometers. So, this intense convergence has led to the arc-arc collision, giving rise to the collision complex made of highly deformed materials. For this figure naman, this timeline shows the geological evolution of Molucca Sea Plate's double subduction system progressing from 14 million years ago to the present day. In figure A, or 14 million years ago, subduction was occurring on the Sangye side beneath the Eurasian plate, and then a slab fragment broke off, possibly due to faulting and dehydration-related weakening. In figure B, or 10 million years ago, subduction on the Sanghe side ceased. The subduction initiated on the Halmahera side, pulling the Molucca Sea plate in the opposite direction. In figure C, 2 or 2.6 million years ago, the Halmahera slab stiffened, suggesting increased subduction activity. The Molucca Sea plate was now being pulled from both sides, forming a complete double subduction zone. And for the last figure, or figure D, this is the current stage or the present day. This region represents a rare example of fully developed arc-arc collision system with slabs retreating in opposite direction. So why this is important? This unique setup offers clues to how oceanic plates are destroyed. It also helps geologists understand complex mantle dynamics, volcanism, and earthquake behavior in convergent margins. So, in the Molucca Sea Collision Zone, one of the remarkable geological features in the presence of a tectonic melange, a chaotic mixture of rock types resulting from intense tectonic forces during the subduction and collision. So within this melange, we find ophiolite blocks, which are fragments of ancient oceanic crust and upper mantle rocks that have been thrust into the Earth's surface. These ophiolite blocks are exposed particularly in Talud Archipelago, Mayo Island, and Tiferi Island. Together, these islands form a ridge that cut across or bisects the collision complex. In the figure, a tectonic melange, including ophiolite blocks, are exposed on the Talud Archipelago and the Mayo and the Tiferi Island, as interpreted as slivers of oceanic crust and trenches sediments uplifted in the fore-arc terrain. These islands form a ridge that bisects the collision complex and generates a free area gravity anomaly height. So, the north of the Tulud Archipelago, in the Mindanao Island region, the convergence manifests itself in a different structural style. Here, oblique convergence of the Philippine Sea Plate generates left lateral strike-slip movement along the Philippine Fault. The Snellius Plateau, which is considered to be the northern extension of the Halmahera Arc, underthrust Talud, causing its uplift, and another tectonic scheme suggests that the Sanghe Trench continues northward up to the east of Miangas, hence the central ridge could be a backstop of the Sanghe subduction zone.
A pleasant day to all of you. I am Bianca May D. Miaga, and for today, we are going to discuss about the tectonic evolution of the Indonesia. Indonesia's tectonic evolution is a complex interplay of geological processes driven by the interactions of multiple tectonic plates. This archipelagic nation is situated at the convergence of several major plates, including the Eurasian, Indo-Australian, Pacific, and Philippine Sea plates. The region's tectonic history has shaped its geological features, including the formation of its extensive volcanic arcs, earthquake activity, and the development of its unique landscapes. Indonesia is a geologically complex region situated at the southeastern edge of the Eurasian continent. It is bordered by tectonically active zones characterized by intense seismicity and volcanism resulting from subduction. Western Indonesia is largely underlain by continental crust, but in eastern Indonesia, there is more arc and phyllolitic crust and several young ocean basins. The Indonesian archipelago formed over the past 300 million years by reassembly of fragments rifted from the Gondwana supercontinent that arrived at the Eurasian subduction margin. The present-day geology of Indonesia is broadly the result of Cenozoic subduction and collision at this margin. Moving forward to the Pre-Cenozoic history of Indonesia. Western Indonesia, notably the islands of Sumatra and Borneo, contains most of the oldest rocks in Indonesia. During the Pre-Cenozoic era, lots of events occurred and became a contributing factor to the tectonic evolution of the Indonesia. These events include the following. First, we have the Sumatra's basement. Sumatra's basement consists of pre-tertiary continental blocks derived from the Gondwana and Cathay-Sea. Next, Cathay-Sean. Parts of Sumatra show a Cathay-Sean floral and faunal affinity, indicating a connection to the Cathay-Sean terrain during the Paleozoic. Moving forward, Gondwana blocks. Significant portions of Sumatra are composed of continental blocks derived from Gondwana, evidenced by glacial deposits and specific flora or fauna. Moving forward to Triassic collision. The Triassic period saw the collision of Gondwana-derived and Cathay-Sean blocks shaping Sumatra's geological framework. This collision led to significant orogenic activity. Next, we have the Mesozoic. The Mesozoic era witnessed further tectonic activity, including volcanic arc formation and the intrusion of granitic batholiths. Java and Kalimantan. Sumatra's geological history is intertwined with that of Java and Kalimantan, all being part of the larger Sundaland region. Their tectonic evolution is interconnected. Next, we have the Borneo, Mesozoic collisions. Borneo's formation involved the Mesozoic accretion of various microcontinental fragments of phyllolites and island arcs onto a Paleozoic core. Next, we have the Sulawesi, Cretaceous active margin. During the Cretaceous, Sulawesi was situated on an active continental margin experiencing subduction and volcanic activity. Lastly, we have the Sundaland, Cretaceous granites. Sundaland's continental core contains extensive Cretaceous granites reflecting magmatic activity during that period. These granites are indicative of a complex tectonic history involving subduction and collision. Indonesia's tectonic evolution is a complex and ongoing process shaped by the interactions of multiple tectonic plates. During the late Triassic to early Jurassic, the breakup of the supercontinent Pangaea began with the separation of the Indo-Australian plate from Gondwana. As well as during the Jurassic to Cretaceous, the Indo-Australian plate drifted northward, leading to the formation of the Tethys Sea. The Triassic period marked the beginning of major changes that were to take place throughout the Mesozoic era, particularly in the distribution of continents, the evolution of life, and the geographic distribution of living things. At the beginning of the Triassic, virtually all the major land masses of the world were collected into the supercontinent of Pangaea. At the end of the Triassic, however, plate tectonic activity picked up and the period of continental rifting began. Moving forward to the Cenozoic era that happened 66 to 23 million years ago, Cenozoic rocks cover most of Indonesia. They were deposited in sedimentary basins in and around Sundaland. There are products of volcanic activity at subduction margins, and there are ophiolites, arc rocks, and Australian continental crust added during collision. Continued northward movement of the Indo-Australian plate and the opening of the Indian Ocean occurred during the early Paleogene. On the other hand, the rifting and the formation of ocean basins occurred as the Indo-Australian plate moved northward, leading to the creation of the Sunda Shelf during the late Paleogene. The Indo-Australia plate is a major plate combining the Australian and Indian plates, but they are widely considered to be two separate plates. The Indo-Australia plate stretches from Australia to India. It also includes the oceanic crust of the Indian Ocean. The northeast side of the Australian plate converges with the Pacific plate. Long ago, Australia, India, and Antarctica were once connected as the supercontinent Gondwana. As part of the supercontinent cycle, India drifted apart, moving northwards. On the other hand, the Sunda Shelf is a prime biodiversity hotspot where some of the planet's most endemic species can be found. This image shows the tectonic movement during the Cenozoic, specifically during the early and late Paleogene. Moving forward to the Neogene period spanning through 23 to 2.5 million years ago. It was a time of intense tectonic upheaval in Indonesia, primarily due to the ongoing collision of the Eurasian, Indo-Australian, and Philippine sea plates. This collision resulted in significant mountain building, volcanism, and the formation of numerous basins and arcs. And now let us examine the key events in specific regions. For Java and Sumatra, the subduction of the Indo-Australian plate beneath the Australian plate along the Sunda Trench is the dominant tectonic process. This led to the formation of the volcanic arc that runs along Java and Sumatra, characterized by numerous active and extinct volcanoes. The ongoing collision continues to cause significant earthquakes and tsunamis in the region. The collision also resulted in substantial uplift, creating the high mountains of Java. Next, we have the Borneo. Borneo, unlike the Java and Sumatra, is situated on the Eurasian plate and is less directly affected by the subduction zones. However, it experienced Neogene uplift and erosion, shaping its present-day topography. Some tectonic activity might have occurred due to the stresses from the nearby plate boundaries, resulting in localized faulting and basin formation. Next, we have the Sulawesi. Sulawesi's complex geology reflects to its location near the junction of multiple plates. It experienced significant deformation and uplift during the Neogene due to the transpressional forces. The island's distinctive shape is a direct result of these complex tectonic interactions with multiple fault systems creating its four peninsulas. Banda Arc. The Banda Arc, located east of Java and Bali, is a complex arc system formed by the subduction of the Australian plate under the Eurasian plate. This subduction is responsible for the significant volcanism and seismicity seen in the region. The arc's curvature and associated back arc basins are the result of ongoing complex tectonic processes. North Moluccas. The North Moluccas are situated in a region of intense plate interaction with multiple subduction zones and complex fault systems. The Neogene saw significant volcanism and deformation in this region, shaping its rock islands and active volcanoes. Lastly, we have the New Guinea. The New Guinea region is characterized by the collision of the Australian and Pacific plates. This collision created the New Guinea Highlands, a significant mountain range. The ongoing collision continues to cause substantial tectonic activity, including earthquakes and uplift. The Neogene tectonic events in Indonesia were not isolated incidents, but interconnected processes driven by the convergence of major plates. The resulting geological features, volcanic arcs, mountain ranges, basins, and complex fault systems have profoundly impacted Indonesia's landscape, biodiversity, and susceptibility to natural hazards. Understanding these events is crucial for managing risks associated with earthquakes, tsunamis, and volcanic eruptions. The ongoing tectonic activity highlights Indonesia's dynamic geological setting and underscores the need for continued research and monitoring.
Now, let's discuss about the key events of Miocene to Pliocene epoch. During the Miocene epoch, which spans from around 23 to 5 million years ago, the groundwork of Indonesia's modern tectonic setting was being laid. This period marked the beginning of significant tectonic collisions, particularly between various microcontinents and larger plates. These collisions triggered the initial movements of microplates like the Banda and Timor microplates within the region. And at the same time, we started to see early signs of crustal extension, especially in the eastern parts of Indonesia, which began forming rift zones and opening of small basins. Moving into the Pliocene epoch, from roughly 5 to 2.5 million years ago, the tectonic activity intensified here. The region experienced stronger compressional forces leading to the uplift of major mountain belts across parts of Sumatra, Java, and Sulawesi. Faulting became more widespread and more active, creating the complex fault system we see today, and also this era solidified much of the current topographic and tectonic structure of Indonesia setting, um, wherein it sets the stage for the Quaternary period. Now, for the tectonic movements from the Miocene to Pliocene epoch, this map shows the Indo-Australian archipelago, highlighting present-day land masses surrounding seas and important geological boundaries. The different colors here represent national boundaries, while the red and orange borders distinguish islands that belong to the Greater and Lesser Sunda Islands. This region during the early Miocene to Pliocene was undergoing significant tectonic reorganization, and as you can see in the map, as the Indo-Australian plate moved northward, it collided with the Eurasian margin, leading to the development of island arcs, formation of straits, and emergence of new landforms due to crustal deformation. Aside from that, the convergence also initiated early microplate rotations and extension in some regions. Over time, this complex interaction began shaping the archipelago into what we recognize today. These early tectonic configurations set the stage for the fragmentation and rotation of microplates along the Indonesia. And aside from that, they also contributed to the initial development of key tectonic boundaries, which are still active today. Aside from that, this figure presents a tectonic reconstruction of the Banda Arc during the early Pliocene, based on Hall and colleagues' work in 2017. The areas shaded in light pink highlight regions that were already highly stretched by this time. Tectonic extension had thinned the crust, particularly in the northern and eastern Banda Arc. Aside from that, this extension was driven by complex subduction processes and arc-continent collisions. And as the Australian plate continued to push northward, parts of the arc were pulled apart, reshaping the arc into its present-day curved geometry. And also, this stretching set the stage for the formation of deep basins and contributed to ongoing crustal thinning and yes, the coastal thinning in eastern Indonesia. Also, the extension of the Banda Arc played a central role in shaping the eastern Indonesia's unique arc-back arc system, and it initiated the structural complexities that continue to define Indonesia's tectonic landscape today. Now let's move on to the next, and this image illustrates an early Miocene continental collision specifically between the western Sulawesi and Sulaspur continents or microcontinents. As these continental fragments converge, intense compression occurred. The collision zone experienced significant crustal shortening, uplift, and deformation. This event marked a turning point in the geological history of Sulawesi, initiating major structural reconfigurations. And also, the terrain that once belonged to separate tectonic blocks began to merge, contributing to the formation of complex landforms and setting up the conditions for later tectonic evolution. Here, the continental collision during the early Miocene was crucial in forming the highlands and structural framework of Sulawesi, and also it marked a major phase of crustal convergence in Indonesia's tectonic history. Next, following the initial collision, this figure shows how the western Sulawesi region entered a phase of extension during the late Miocene to Pliocene. This was triggered by lithospheric delamination, and this delamination or lithospheric delamination pertains to a process where dense lower part of the lithosphere detached and sank into the mantle. As this happened, the remaining upper lithosphere became buoyant and began to stretch. This extension led to the development of basins, thinning of the crust, and reactivation of faults. Essentially, what began as a compressional tectonic setting transitioned into an extensional one, significantly altering the landscape of Sulawesi and contributing to its current tectonic complexity. And here, the lithospheric delamination and resulting extension highlight a transition from compressional to extensional tectonics in parts of Indonesia. This shift enabled the formation of deep basins and influenced the ongoing microplate dynamics in Sulawesi and surrounding regions around Indonesia. Now, for the Quaternary to present, which is approximately about 2.5 million years ago until present, um, Indonesia remains one of the most tectonically active regions on Earth. The ongoing subduction of Indo-Australian Plate beneath the Eurasian Plate fuels constant geological activity. This includes active volcanism and earthquake generation or earthquakes, especially across Java, Sumatra, and Sulawesi. Um, the map at the right part of this presentation shows and illustrates the Indonesian volcanic arc system based on Hamilton 1979, and each open circle here represents an active volcano, and as you can see, they form a long chain parallel to the subduction zones. And also, this active volcanic belt is known as the Sunda Arc, and it's a direct result of the subduction process. Also, subduction not only causes volcanoes to form but also produces intense tectonic deformation, which shapes the island's current structure and driving continuous land uplift, basin formation, and crustal adjustments. And now, this map shows the present day tectonic features of Indonesia. Today, Indonesia stands as a complex tectonic puzzle, and it is made of over 18,000 islands stretching more than 5,000 kilometers from west to east. Also, it lies right at the intersection of three major tectonic plates such as the Eurasian Plate, the Indo-Australian Plate, and the Pacific Philippine Sea Plate. In the western part of Indonesia, the boundary between the Indian and Eurasian plates forms the Sunda Trench, and this trench is the site of intense subduction, and just inland from it, we find the Sumatran Fault, which is a major right lateral strike-slip fault. This fault accommodates horizontal movements caused by the oblique convergence of the plates. Additionally, Most of the tectonic deformation in Sumatra occurs in the region between the trench and this fault. But as we move eastward beyond Java, things become even more complicated because here we enter a broad tectonic suture zone nearly 2,000 kilometers wide, which involves numerous microplates and multiple subduction zones. And this includes prominent faults like the Sorong Fault, which is a left lateral strike slip fault, which stretches from New Guinea to the Sulawesi. And also, according to the GPS data, the relative motion between tectonic blocks in Indonesia is among the highest in the world, often exceeding several centimeters per year. This high rate of movements explains the frequency of earthquakes, volcanic eruptions, and crustal deformations that characterize the region today. In short, Indonesia's unique geology is shaped by the constant movement of multiple tectonic plates, creating everything from towering mountains to powerful earthquakes. These dynamic processes not only define the landscape but also remind us of the risk of living in such an active region. So that's it for our presentation. Thank you for listening, and I hope this gave you a clearer view of the Indonesia's tectonic history.